we will be looking closely at how to represent numbers in hardware and in Verilog. Remember, in current digital systems, we only have zeros and ones. Conceivably, we could have more discrete levels, but there hasn't been any benefit, so we have zeros and ones. If we had to think in terms of zeros and ones ourselves, we would go crazy. Imagine trying to implement a Fourier transform only thinking in terms of zeros and ones. The way we have evolved is that we develop mathematics. Mathematics gives us a tool for understanding algorithms, signal processing algorithms, image processing algorithms, and so forth. We are used to using mathematics, we are used to using real numbers, complex numbers, etc. We are not used to using binary numbers. So we need some way of going from our algorithms written in terms of real and complex numbers and translating them into binary representations that FPGAs can implement. And that's why register transfer level is such a useful tool. It serves as a bridge between the mathematical world that we understand and the binary world that hardware understands. When we write register 70X in Verilog, we can understand this in at least two different ways. We can understand it as X just contains an 8-bit binary number, or physically, X is a series of 8 wires. We could also choose to understand this as representing a number between 0 to 255. We don't have to, but as I said before, a lot of the things we want to implement on FPGAs come from algorithms. These algorithms came from signal processing people and so forth that developed them using real and complex numbers. You discretize real numbers to get integers, and that's why we often like to think of a register 70X as being an integer between 0 to 255. If we do decide that we will treat binary numbers as integers, then we are able to write things like assign z equals to x plus y. That's something that both we understand and Quartus understands. It can translate that into an operation using only zeros and ones. As we know, addition is not the easiest operation to implement on zeros and ones. We've learnt in the labs how we can do it using half adders and full adders. We've learnt that conceptually it's simply done by writing down the truth table and then finding the logic circuit that implements that truth table, but it might become quite complicated to do by hand unless you break it up into half adders and full adders. Nevertheless, this is just a single short statement in Verilog that implements quite a complicated digital circuit. And this is the benefit of working with mathematics. It's a middle ground. Humans can understand it, and a machine like Quartus can translate it into digital hardware. To elaborate, what we're really saying is that when we write z equals x plus y in Verilog, it means that the number that z represents, so z will have been defined somewhere as a register with a certain number of bits. It's just a sequence of zeros and ones, a finite sequence. But we can choose to give it a representation. We can choose to say, oh yes, if I write out those bits in a certain order and treat it as binary, I can convert that to decimal and get a number that we understand. Therefore, z equals x plus y means take the wires that represent x, translate that into a number that us humans understand, do the same for y, add those two numbers together, and then work out how to represent that number using some wires, and that's what the wires making up z are going to be set equal to. Although we have primarily just used one way for representing numbers, in fact we've learnt two ways. We can represent the number 5 in a register x in the first way or in the second way here. Both of them are using 4 wires to represent a number. They can represent a number between 0 to 15 because 2 to the power of 4 is 16. And we know that the representation is obtained by using decimal to binary conversion or vice versa. So if we are storing the number 5 there, then we take the number 5 in decimal and we write it in binary as 101. The question remains though, is there any difference in how that's stored in X and in Y? If we take the number 5 and write it using 4 bits in binary, then we'd normally write 0101, where this is the least significant bit and this is the most significant bit. And normally when we write numbers, we have the most significant bit on the left. If I write the number 500, then I put the most significant bit on the left. That's just the convention humans have adopted. So here is how we represent number 5 in binary, with this being the most significant bit, this being the least significant bit. Now the difference between these two representations is that in the first representation, x3 contains the most significant bit. That is, x3 will be equal to 0 and x0 will be equal to 1 in this representation here. In the second representation, it's round the other way. Y of 0 is the most significant bit, so therefore it will contain 0, and y of 3 being the least significant bit will contain a 1. So there is a difference in how these numbers are going to be represented if we declare them 30 versus 03. However, they still represent the same number, and we will come back to that shortly to see why that's important to remember. It simplifies our understanding of things to remember that. First, let's clarify what we said before. If we write that y of 30x equals to 5, then that means that this will equal 0101, because x of 3 is the most significant bit and x of 0 is the least significant bit. But if we write y at 03, y equals 5, that means that y of 0 is the most significant bit, so it's going to be equal to 0, and y of 3 is the least significant bit, so it's going to equal 1. And if I reverse the order, then of course I get that y3 down to y0 is equal to 1010, which is different from this one here. So there is a fundamental difference in how these numbers are being represented. It might be worthwhile remembering what happens in a programming language such as C. We can write z equals x plus y in C, and we expect it to work. We don't care about, well, often we don't care about how x and y are represented. We just want to make sure that however these numbers are represented in C, we get that z equals x plus y according to the rules of arithmetic. Because C runs on a computer and computers are digital, then actually x, y and z are all going to be stored in binary notation somewhere, well, using zeros and ones in memory. We can look up how it's done. It's actually a bit different on different computers. The number of bits used can differ. The ordering in which the bits appear in memory can be used. There's Little Endian and Big Endian notation, for example. But the point is, when we program in C, x, y and z are being stored using zeros and ones, but we just expect z equals to x plus y to work. And that's exactly the situation in Verilog. When we write z equals x plus y, it will do what we expect it to do, just like how it does it in C. We can work out how it's being represented if we wanted to, but first and foremost, z equals x plus y agrees with what we expect it to equal. I have been belabouring that point because it makes it easier to work out the answer to this test. You see, when we get down to this point here, I don't have to worry about how x and y are being represented internally. I just have to see that when I write z equals x plus y, I take x, I take y, and I add them, and I know that z's equal to 10. This is irrespective of how x and y are actually stored in memory. That one stored this way, the other stored that way is irrelevant. They both represent 5, and 5 plus 5 is 10. That's the shortcut that I was trying to emphasize before. Therefore, to answer this question, we just have to work out how, if z equals to 10, how is that going to be stored in memory? So the first thing we do is we take the number 10, we work out how to write it in binary. We know that this is the most significant bit. We know that this is the least significant bit. We look at whether it's 03 or 30. Written this way round, we know that bit 3 is the most significant bit. Therefore, we know the answer is given by this. The next topic is negative numbers, and I come back to the first principle again. If I write, and now I've introduced the signed keyword, and we will explain that later, but intuitively this allows x, y and z to store negative numbers as well as positive numbers. We will get to that soon. But here, if x equals negative 12 and y equals to 15, then z equals x plus y, we expect z will be equal to minus 12 plus 15, which is equal to 3. Irrespective of how these three numbers are being represented in binary, irrespective of that, we expect that z is going to represent the number 3. So if we run this program, and I encourage you to find an online Verilog simulator and run this program to see what happens, we expect to get coming out here that x is negative 12, y is 15 and z is 3. It should just work. We find that it does indeed work, but then we can ask, what do we need to be careful of? In fact, there's a few things we need to be careful of. Verilog can be quite tricky if we're not careful, but if we are careful, things become easy. So I will present some of the tricks, but it's easy to avoid the tricks, and then we don't have to worry. Before discussing how Verilog represents negative numbers, we're actually going to derive it ourselves. But before we even do that, it's worth saying that first of all, we can choose any way to represent numbers. There's nothing stopping us from declaring that 00 will be used to represent the number 1, 01 will be used to represent the number negative 1, 10 will be used to represent 0, and 11 will be used to represent 2. We can do that. We just have to write down on a piece of paper our method of encoding numbers and then stick to it. There's nothing stopping us from doing that. So why is this a bad idea? Basically, it's bad because we then have to do everything ourselves. We could not use anyone else's code because anyone else's Verilog code would be designed using the normal way of representing numbers. Our way is different. It's incompatible. We'd have to develop everything ourselves. And doing fast addition, fast multiplication, etc. is non-trivial. We'd have to spend months, years maybe even, coming up with fast algorithms to work with our chosen way of doing things. So it's better to fit in with how other people are doing it. Even if it's not always the most efficient, it saves time in the end because we can reuse what other people have done. So with this line of thinking, we can motivate a way of representing negative numbers by saying, is it possible that if I already have a circuit for adding numbers together in binary, can I keep using that circuit to also add negative numbers? Is there such a representation out there for representing negative numbers such that existing adders will still work? That's the motivating question, and it turns out that yes, there is. And that's why there's a clear winner, most of the time anyway, in how we're going to represent negative numbers in binary. We don't have to do it the way we're about to discuss, but it's often the most convenient way of doing it. The way we are going to do it has got a nice name. It's called 2's complement, and it has the benefit of working with existing adders. We don't have to change our adder circuits, and they will still be able to add numbers even if we move to this new representation for representing numbers. So to derive 2's complement, because I always find it's easier to learn by trying to derive something rather than just to try to derive it, we say that, well, what we want if existing adders work is that the way we will represent -1 must be such that if I try to add -1 to 1 on an existing adder, I will get the answer 0. And similarly, however I represent the number -2 should be such that when I add 2 to it, I get 0. So I can now try to figure out the representations for -1, -2 and -3 based on these obvious requirements here. So to represent -1, we want to find a 4-bit number such that when I add it to 1, I get 0, because -1 plus 1 equals to 0, so whatever fits in here should be my representation for -1. And so it doesn't take much thought to realise that 1111 fulfills this. 1111 plus 0001 gives me 0. Yes, there is a carry, but we're throwing the carry away here. This way we can reuse our adder circuit and things work nicely. If things are going to work, and that means that everything is consistent, then I have at least 2 ways of finding out how to represent -2. The first option is to do the same as what I did on the previous slide. I can ask what number plus 0010 gives me all zeros. But if everything is working properly, if it's possible to come up with a representation that we're after, that would mean that I get the same answer by taking -1 and adding it to -1. That should give me -2. And so if we take this option, here I write down -1. We found that 1111 seems to represent -1, and if I add it to itself, then I get 1110. And so if it's possible to have a consistent representation, then 1110 must represent -2. Note that if we write this using our usual convention, then 1111 is equal to 15 and 1110 is equal to 14, we find that we're just counting backwards. So 13 is going to represent -2, 12 will represent -3, and so forth. This is what we've essentially derived. Now if we do this, the question is, when do we stop? I can count all the way back to 0 and represent negative numbers from -1 all the way to -15, but then I have no positive numbers left. So the question is, when do we stop? Well, let's consider 4 bits as we have been doing. With 4 bits, I can represent 16 numbers. I can choose what 16 numbers, but 2 to the power of 4 is 16. There's only 16 different things I can represent with 4 bits. It seems natural to take 0000 as 0, and it's natural to take 1111 as -1 since I want at least some negative numbers. But the question is, what is the largest positive number and what is the smallest negative number? Where do I stop? I can choose. Do I go from -1 to 14? Do I go from -2 to 13, etc.? Where do I stop? It seems sensible to stop halfway. In other words, ideally, I want to represent numbers from -7 to 7, or from -8 to 8, for example. Equal number of negative and positive numbers, not counting 0. But we can't quite get there. If I have got 16 numbers, 4 bits gives me 16 different things, and I have a 0 in there, that only leaves 15, and 15 is not divisible by 2. So I can either go from -8 to 7 or from -7 to 8. That's the closest to halfway I can get. So now the question is, which one of these two should I choose? And it turns out that there's a nice choice that we can make. Given a number representation, so if I write down just a number randomly, we can ask, is this number negative or positive? Now it turns out that if we choose the range to be -8 to 7 as opposed to -7 to 8, then using the representation we've discussed before and using this as our range, it turns out that the most significant bit tells us exactly the sign of the number. If this is a 1, the number's negative. If this is a 0, it is positive. And to see why, just remember with 4 bits, if I count forwards positive, I get to 0, 1, 1, 1. That represents the number 7. And we see that the numbers 0 to 7 all have got a 0 out the front. They are positive numbers. Now when I go to represent the numbers -1 to -8, it turns out that they are given by, well, we know that this is 1, 1, 1, 1, and then I count backwards and it'll end up with 1, 0, 0, 0 here. So all our negative numbers will have a leading bit being equal to 1. So this choice here from -8 to 7 means that the leading bit tells us the sign of the number, and that's why we choose -8 to 7 and not -7 to 8. At this point, if you believe me, then we can represent negative and positive numbers in such a way that addition still works in the usual way. And we can essentially find that number by starting at 0 and either adding 1 or -1 the appropriate number of times. It turns out everything does work. In fact, if you like mathematics, you can show it's related to modulo arithmetic, or clock arithmetic as it's informally known. But given that it all works, and it does work, we can ask, is there a fast way of going from a decimal number to its binary representation in 2's complement, and vice versa? Given a binary number in 2's complement notation, can we quickly find what decimal number it corresponds to? And it turns out there is a very simple rule for doing this, and it is the following. In fact, to be precise, what we do is if we want a negative number, then we first write it as a positive number and then apply this rule to convert it to a negative number. Or conversely, if we're given a negative number, we can apply this rule and get back the corresponding positive number. It turns out that this rule is dual to itself, so you apply it twice and you're back to where we started, but I'm getting ahead of myself. Let's just start. If I want to convert from a positive number to a negative number, then all I do is write the number in binary, invert every bit, and what I get is known as 1's complement, and then I just add the number 1, which gives me 2's complement and helps explain why we're called 2's complement. So here's a simple example. I want to express -5 in 4 bits using 2's complement notation. So I start off and write down the positive version. 5 is given by 0, 1, 0, 1. That's the first step. Now the second step is to invert every bit. So I get 0, 1, 0, 1. And then the last step is I just add 1. So I get 1, 0, 1, 1. And this represents -5. And if we so desired, we can check. If I take 1, 0, 1, 1, and if I add 5 to it, then I should get 0. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 0 plus 1 plus the carry is 0, carry 1. And 1 plus 0 plus the carry 1 is 0, carry 1. And we ignore the final carry. And so indeed we end up with 0. So this is the correct answer. And while we're on this page, let me just go in the reverse direction. Say I'm given the number 1011. I know by looking at the most significant bit that this is a negative number, so I know I have to convert it to a positive number. Now I could do the opposite. I could subtract 1 and then invert every bit, but it turns out that I can actually just do this again and I'll get the same answer. It's just one of those nice things that happens. So if I invert every bit, I get 0, 1, 0, 0, and then I add 1 to get 0, 1, 0, 1. And I'm back to where I started. An example of going in the reverse direction is the following. Let's say we're given this 8-bit number and we're told it's a 2's complement number. If it's not a 2's complement number, we convert it normally and we'd get a large positive number. But if we're told it's 2's complement, then we look at the most significant bit, we see it's a 1, and so therefore we know that this is a negative number. This means we need to apply our rule to transform it from negative to positive. So I should just say, if we had a number that started with a 0, then we know it represents a positive number and we just convert it normally. That's just a simple binary to decimal conversion, nothing else there. The only issue is if the leading bit, if the most significant bit is a 1, then we need to first apply our rule to get the corresponding positive number, then we convert that number normally into decimal, and then we add a negative sign. So back to where we were, we're given this number here. We see that it's a negative number because its most significant bit is a 1, therefore we apply our rule. First we invert every bit, and then we add 1. And now the final step is that we simply take the number we got here, and this is the positive version of this number here. We convert it to decimal in the usual way, and then we add a negative sign to it. And so now we know that this number represents negative 46. Or precisely, this binary number in 2's complement notation represents negative 46. Although many people don't consider it, they should consider, when programming in C, what is the largest number that can be stored in an integer, or the smallest number. All registers are finite, and when you're doing important computations, you need to know these bounds. On an FPGA, we usually try to use a small number of bits to save space, save flip-flops, and so it becomes even more important to know what are the largest and smallest numbers that can be represented using a certain number of bits. Let's consider the largest number that we can represent in 2's complement notation. Of course, it depends on the number of bits. If we're told we have 8 bits to work with, then to figure out the largest number, well, that means the largest positive number, we know that that number has to start with a 0 because the most significant bit tells us the sign of the number, and that gives us 7 bits left. And if we want the largest positive number, then we know that these 7 bits represent what they normally do, so therefore the largest number is given by all ones here, or in other words 127. In general, if I have an n-bit number, then the largest 2's complement number I can represent will be 0 followed by n-1 bits. And therefore, the largest number I can represent is 2 to the n-1 minus 1. What about the smallest number? Well, remember how it works. If I had 4 bits, then 1111 represents negative 1, and then I just count backwards in decimal, that's 15. So 1110 represents negative 2, that's 14. I'm counting backwards. If I count backwards, but remember I have to keep the most significant bit a 1 to represent a negative number, we find that the smallest number I can get, or the most negative number I can get, is 1000. Or in general, if I have n bits, the leading bit will be a 1 and all the other bits will be a 0. This gives me the smallest possible number in 2's complement, and we can easily work out that the value of this number is going to be minus 2 to the n-1. We now move on to the next topic, and that is how to use negative numbers in Verilog, and we do have to be careful here because Verilog has got some interesting tricks up its sleeve. In a nutshell, there are only 2 things to worry about. Firstly is allocating enough bits, because we need an extra bit for the sign, and that's easy to forget if you're not used to dealing with signed numbers. Now the second one sounds simple. The rule is never compare a signed and an unsigned number in an if statement. The problem is it can be difficult to work out when you're new to this what is a signed number and what is an unsigned number. That's why this one's actually quite tricky. But at a high level, the rule's simple. Never compare a signed with an unsigned number. For example, one would expect that this is going to work. I've got an x representing an 8-bit signed number, and I just want to know if x is less than 10 or not. It seems really straightforward, but unfortunately Verilog is going to trick us here, because according to the Verilog standard, this is an unsigned number. This is a strictly positive number with no sign, and so although x is signed, Verilog is going to see that this guy is unsigned and therefore treat everything as unsigned. So if x contains a negative number, it will not be treated as a negative number, it will be treated as a positive number, and therefore this is not going to work as expected. To elaborate, imagine that our number x was representing -1. That means that stored inside x is 1111, 1111. We know that this is -1 in 2's complement. Then when we get to the if statement, because this is an unsigned comparison, we need to ask what number x represents as an unsigned number. Now, as an unsigned number, x is going to represent the number 255. And here we're comparing, is 255 less than 10? And the answer is no. So while we expected this if statement to evaluate to true, it evaluates to false, because Verilog treats this as an unsigned comparison. It treats whatever is stored in x as an unsigned number. 1111, 1111 represents 255, and that is not less than 10. How do we fix this? Well, we just have to make sure that Verilog understands that we want a signed comparison. Because x is signed, we just have to make sure that the number we put here is a signed number. So the question really is, what numbers do Verilog treat as being signed? One thing Verilog treats as being signed is anything that contains the S right here. That signifies signed. It's very clear that this is a signed number. So therefore, when I write this here, it means I've got a 5-bit number. S here means it's signed. To be pedantic, it means we're going to use 2's complement notation to represent it. So this means the 5-bit 2's complement number that represents 8. If I write it like this without a leading number, then as far as I can tell from reading through the Verilog standard, there is no default bit length, but in practice, the systems I've used, such as Quartus, default to 32 bits if you omit the leading number. Now, Verilog is a little bit unusual, maybe due to its long history, but the number 10 without anything in front of it, without a D for decimal, that's actually interpreted as a signed number. Now, personally, rather than memorize all the rules, which you could do, it might be better to avoid any ambiguity and always use S if you want a signed number. So if you do like rules, then remember that both 5 and -5 are signed, but prime D5 is unsigned, and even minus prime 5D5 is also unsigned. You may well ask, why is this unsigned? There's a negative sign there. Well, this is how Verilog works. Verilog first sees that we've got prime D5, and Verilog says, aha, you've written a D, you have not put an S in here, therefore this is an unsigned number that represents 5. Now, because I did not specify the number of bits here, then different implementations will have a default. Let's say it's 32 bits, so therefore this will actually correspond to, well, I don't want to write them all out, but I'm going to end up with this number here, where in total it's 32 bits long and it starts with lots of zeros and finishes in 101. That's what prime D5 is going to give me. This negative sign here is treated by Quartus as an operation. This is telling Quartus to take the 2's complement of this number here. It's not saying that it's going to end up being a signed number. No, that would be too sensible for Verilog. Instead, it says, I'm dealing with an unsigned number here. If I see a negative sign, that just means I want to perform a 2's complement operation, but I'm not going to change the sign of the number. I'm not going to change the representation. I'm just going to carry out the 2's complement. So in other words, when we encounter this negative sign here, we perform the 2's complement. How do I do that? I invert all the bits, so I end up with this, and then I add 1, and so therefore this number is going to be what this becomes, but it's going to be this positive number. It's not a signed number, it's an unsigned number by convention. We now know that this is not going to work as expected. Y is an unsigned number, therefore this if statement will be made into an unsigned comparison. Even if x represents a negative number, that will be ignored. X will be treated as representing a positive number when doing this comparison here. So the way to fix it is that we can actually use these Verilog functions to... Now these don't do anything in terms of hardware. They're not hardware functions or anything. All it's doing when we use something here is telling Verilog to, if I do signed y in here, that's telling Verilog that I want to treat y as a signed number. So I can use that in this if statement here, as we'll see on the next slide. So this is how we implement our if statement here. We convert y to being signed, and then everything will work nicely. We just have to be aware of this. If we're using signed numbers, everything must be signed when doing a comparison for it to work. And this is how we can make a register signed if it originally is not signed. Remember, this is just about how we represent numbers. The number inside y doesn't change. It's just the meaning that us humans ascribe to that number will change depending on whether we say that it's an unsigned number or whether we're saying it's a signed number in 2's complement. Depending on the meaning we give to it, that will determine how we want Verilog to understand this if condition here. This if statement is our bridge. It's Verilog's way of saying, I'm going to treat these numbers the way you humans are used to treating them. But tell me if you want to treat them as being positive numbers or if you want me to treat them as being 2's complement numbers. Let's see how we go with this challenge. We start off with x equaling -1. So we know that -1 in 2's complement is going to be 1, 1, 1, 1. Y is equal to x. Now, notice that y is 8 bits long, whereas x is only 4 bits long. So what happens here? Well, we go back to rule number 1 at the start of this lecture. Rule number 1 is Verilog should do what we expect it to do. If we do y equals x, and if x equals to -1, then we expect y to be -1. So that means we expect that y is going to be equal to 1, 1, 1, 1, 1, 1, 1, 1, because that is how we represent -1 using 8 bits in 2's complement notation. And if we run this, you'll find that this is exactly what happens. For those that cared, we could ask the question, how did Verilog know to extend our number to keep it negative? Because in the past, when we've assigned a 4-bit number to an 8-bit register, then we know that the leading bits are just going to be filled with zeros. And so we could perhaps ask why do we not get a value for y being 0, 0, 0, 0, 1, 1, 1, 1. That would be the wrong answer, so luckily this does not happen. But if we cared, what's Verilog actually doing? Why does this work? Why do we get the correct answer that we do? Well, it turns out that things work very nicely because all Verilog has to do is do a sign extension. In other words, if we start off with a 4-bit number and we want to extend it to 8 bits, all we do is we look at the most significant bit and extend that. So if it starts with a 0, we put all zeros out the front. If it starts with a 1, we put all ones out the front. And this works beautifully. Remember, if it starts with a 0, it represents a positive number, and so indeed we just want zeros out the front. If it starts with a 1, it's a negative number. So what we want is to end up with the corresponding negative number. And you can show that we get the right number just by adding these leading ones here, and it works out beautifully. So we have yet another benefit of 2's complement notation. To summarise this lecture, we've looked at how numbers are represented, and there are 2 standard ways we can represent a number. If it is an unsigned number, we represent it the way we're used to, where we just convert it between decimal to binary in the usual way. If it's a signed number, then normally we use 2's complement notation to represent it. That means that if it's a positive number, I represent it normally, but I make sure that the leading bit is a 0. If it's a negative number, what I do is I first write that number in binary as a positive number, and then I convert it to a negative number by inverting all the bits and adding 1. This will make the most significant bit a 1, provided I have enough bits. Otherwise, I can't represent the number. It falls outside the range I have with the number of bits I have. The most important thing is to remember that whenever we do an operation in Verilog, such as an addition or an if statement or so forth, that it is using the representation of the number. And so it doesn't matter how we mix and match our different representations, the order in which we've got least significant bit to most significant bit, etc., we should end up getting the correct answer. Now, the only exception is when we come to doing comparisons. And for some reason, Verilog states that if you try to compare a signed and an unsigned number, I'm going to treat everything as an unsigned number. This means that we just have to be very careful whenever we do a comparison to make sure that if we want it to be a signed comparison, that both sides are signed. If we're just writing a number, we can do this by making sure we have got the S modifier there to make it a signed number. Just putting a negative sign out the front is not enough. We saw an example where we wrote negative prime D5 and emphasised that that is not a signed number, that's an unsigned number. Anyway, with comparisons, they will work correctly as long as both sides are signed or both sides are unsigned. And that's it.